Finally, we need to address a technical issue that we hinted at when we normalized the weights of data points to start to 1 over n, when we had uniform weights, which is the issue of renormalizing the weights of the data points throughout the iterations. So for example, if we take a data point xi, suppose that it's often a mistake, we're multiplying its weight by a positive number again and again and again. Let's say 2 times 2 times 2 times 2, and that weight alpha can get extremely large. On the other hand, if you take a data point xi that's often correct, you multiply by some number less than 1, so say a half, so you keep multiplying by a half, and that weight can get really, really small. And so this problem can lead to numerical instabilities in the approach. And so, your computer might not, behave very well with all this crazy weighted data. And so what we do is after each iteration, we go ahead and normalize the weight of all data points to add up to 1. So basically, we divide each alpha I by the sum over the data points of alpha I. So this approach keeps the weights in a reasonable range and avoids numerical instability. So let's summarize the AdaBoost algorithm. We start with even weights, uniform weights, equal weights for all data points. We learn a classifier f of t. We find its coefficient depending on how good it is in terms of weighted error. And then we update the weights to weigh mistakes more than things we got correct. And finally, we normalize the weights by dividing each value by this total sum of the weights. And this normalization is of practical importance. So this is the whole AdaBoost algorithm. It's beautiful, works extremely well, really easy to use.